Let's just jump right into it. Today, we're unpacking something we literally look at every single day, usually without a second thought. It's probably the most common question in the world, the kind a kid asks, and then suddenly, as adults, we realize we can't actually give a straight answer. We're talking about the physics of sky color. And specifically, we're going to break down this massive, fascinating optical illusion that is happening right above our heads.
So here's the big question to kick off this explainer. Why exactly does the sky turn from this brilliant, crisp blue during the day into that deep, fiery red when the sun sets? Now, if you're sitting there thinking, oh, well, the sun is just changing temperature, or maybe, it's just dust in the air, I'm going to playfully tease you right now, because the answer is probably not what you think. Let's just geek out over this for a minute, because what's actually happening up there is absolutely mind-blowing.
Section 1. The atmosphere's greatest trick. Okay, we're going to completely shift how you view a sunset right now. Because to understand this, you really have to look at the sky not as just some empty space, but as an active participant in a giant magic show. The sun is absolutely not changing color. That fiery red ball dipping below the horizon, it's emitting the exact same light it was at high noon. The whole thing is entirely our atmosphere playing this massive, beautiful trick on your eyes. And to figure out how this trick works, we've got to talk about what sunlight actually is before it even reaches us.
Section 2. Sunlight is a hidden rainbow.
So the secret of sunlight is that even though the light beaming down looks perfectly white to us, it's actually a hidden mixture of all the colors of the rainbow, just packed together. But here is the kicker. These colors do not travel in the same way. Light travels as a wave, right? And each color has its own unique physical shape. On one side of the spectrum, we've got red light. Red light travels in these long, lazy waves. Think of it like a really gentle, rolling ocean swell. On the other side, we have blue and violet light. Now these travel in short, choppy waves, kind of like the frantic splashing water in a crowded swimming pool. And this difference in their physical wave shape, that's the entire key to our mystery here. Section 3. The short, choppy blue waves. Right now, as we speak, these short, choppy waves are on a collision course with our planet. But before sunlight can actually hit your eyes, it has to navigate Earth's obstacle course. Our atmosphere isn't just empty air, right? It's a dense, completely chaotic minefield of gas molecules. Specifically, it's packed mostly with nitrogen and oxygen. So just picture these light waves, the lazy reds and the frantic, choppy blues, racing in from space, and then bam, they slam into this invisible wall of gas molecules wrapping around the Earth. So what happens next?
Well, this brings us to a really cool scientific concept called Rayleigh scattering. When those short, choppy blue light waves enter the atmosphere, they just happen to be the absolute perfect size to crash straight into those nitrogen and oxygen molecules. And when they crash, they bounce. They get scattered in literally every single direction, pinging from molecule to molecule like this frantic game of cosmic pinball. But the longer, lazy red waves, they mostly just glide right over and through these molecules completely uninterrupted. It's the short blue waves that get trapped in the pinball machine, scattering wildly across the whole sky.
So the absolutely crucial point is this. When you walk outside at noon and look up, you are not seeing light traveling in a straight line from the sun to your eye. Actually, scratch that. It's more like you are looking at an atmosphere that is completely saturated with short, choppy blue light waves bouncing around in midair. Your eyes are catching that scattered blue light coming from every single corner of the sky. That's the magic trick. The daytime sky is blue simply because our atmosphere is acting like a giant, glowing blue filter.
Section 4. The thick sunset filter. So if the daytime sky is just a giant blue filter, what on earth happens at 7 p.m.? This is the climax of our physics story. Let's walk through the physical journey here, step by step. Number 1. The sun lowers on the horizon. Number 2. Because of this super low angle, the sunlight now has to travel through a much thicker layer of the atmosphere to reach your eyes, compared to when it was just shining directly overhead at noon. Now remember our cosmic pinball machine? Number 3. Because this layer of atmosphere is so incredibly thick, the short, choppy blue light crashes into so many gas molecules that it scatters away completely. I mean, it literally runs out of steam before it even gets close to you. So what's left? Number 4. The long red and orange waves. They finally get their moment to shine.
Only the long, lazy red and orange waves are strong enough and actually have the endurance to push through that incredibly thick sunset atmosphere. The blue light, it's been entirely stripped away, just filtered right out by miles and miles of extra air. But the red light just keeps rolling along, gliding past the gas molecules right into your eyes. You are essentially looking at the exact same sunlight,
but it has been aggressively filtered. It's honestly like the red and orange waves just ran an ultramarathon, and they were the only ones tough enough to cross the finish line.
Section 5. Measuring distance with color.
Okay, this next concept is a total paradigm shift. It will fundamentally change how you look up at the world. Think of a blue sky. That represents daytime, meaning light is traveling through a relatively thin layer of air straight down to us. Now think of a red sky, representing sunset. Here, light is traveling horizontally through a massive, ridiculously thick layer of air. The color you are seeing isn't a physical object, it's not a pigment. It is literally a visual representation of atmospheric density and distance. Blue equals a short trip through thin air. Red equals a long, exhausting trip through thick air.
I actually want to read this direct quote from our source material, because it just nails it perfectly. The color of the sky is essentially a measure of how far light has traveled through our air. I mean, just let that sink in for a second. When you are out there watching a sunset, you're basically looking through a massive atmospheric filter. You are watching light that has traveled so incredibly far through so much air that every other color has literally been beaten out of it, leaving you with only those deep, vibrant reds and oranges.
So, I want to leave you with this provocative thought as we wrap up this explainer. The next time you look up, whether it's a crisp Tuesday morning or a fiery Friday evening, ask yourself, what distance are you actually seeing? Are you looking at the short, chaotic bounce of thin midday air, or are you witnessing the long, deep marathon of a sunset? You see, you're not just looking at colors anymore. You are looking at the literal physics of light making its incredible journey to your eyes. Keep looking up, everyone, and definitely stay curious.